Good morning, everybody. Welcome to sunny Tuesday morning at Chem 11:05 with your host, me, Dr. White. Hi, everybody. We got a lot to do, so let's get to it. First of all, before I switch to another, let me remind you, make sure you've done test number 4 and hand it in today by 1 or 2 p.m. Get it in. Also, make sure you do the lab that was due last week. Get it in now. It's the end of the semester, just about. Yeah, it really is. Get your labs in. All right, let me remind you. Oh, excuse me. Let me remind you on Monday, the 15th of this month, which is next Monday, I will be giving a comprehensive 11:05 final exam online. You'll download the PDF, password protected PDF file, say that 5 times quickly, for the final exam from the assignment area Blackboard on Monday, the 15th around 9 a.m. I will send out a email with the password to open up the final exam PDF file. You'll have until Tuesday, 2 p.m. to finish the final exam and upload it as a single PDF file. Should take you about 70 minutes, maybe a little longer to finish it. But if you need it, take up to 3 hours. And I'm not going to be there with a stopwatch. I used to own a stopwatch. I wonder where it went. But anyways, the final exam will cover all the material in this semester's Chem 11:05. The final exam has 27 problems on 8 pages. Some of the problems are multiple part. There are 5 multiple choice. The point breakdown for material from test 1, 16, test 2, 44, test 3, 29, test 4, 21. It adds up to 110. So there's 10 bonus points. You'll need a scientific calculator. I reserve the right to subtract up to 50 points. Anybody doesn't follow instructions, anybody doesn't upload your final exam on time as a single PDF file. And by the following Friday or earlier, I will post in Blackboard your final exam scores, all your totals, all your labs, and I will also have your grade. Now, the official school system for posting grades usually takes about 24 hours after I put it in the system for you to see it. But the grade you see in Blackboard for Chem 11:05 will be the same grade I will be putting in there. Next week will be finals week, the week of 5/15/23. So there's no Zoom meetings, no labs. I will have office hours though. And speaking of office hours, don't forget today, Tuesday, and tomorrow, Wednesday, from 6 to 7:15, I have my office hour on Zoom. If you need help, stop by. Or if you just want to say hello to Dr. White, stop by. All right, in keeping the way I've changed things, let's do today's lab. All right, on your screen, you'll see today's lab, Lab 13, Fundamentals of Chromatography. Please notice, just do activities 1 and 2. I'll say that again. Please notice, just do activities 1 and 2. And here's a couple of videos you might want to watch that'll help you. And remember, you must include one selfie of you doing one step at a lab or holding some chemicals from the lab, or you'll get 0 points. That's a big 0 points for the lab. And that's chemistry department regulation or rule for online labs this semester and probably next semester, which I think is a good rule. All right, let's take a look. Let me open up the lab. Give me a All right, today's lab deals with fundamentals of chromatography. What the heck is chromatography? Let me remind you, for this lab, as always, you should wear your safety goggles, gloves, especially gloves, and safety goggles when you're working with the dyes, and also the Kool-Aid too, but really the dyes, and I'll tell you a story in a little while about food dyes, and they can be really uh, dangerous. And wear an apron to keep your dyes off your clothes. Now, various things in our life have colors that we use and that we buy. And those colors are put in those products by color additives. And when you look at something that's yellow or red, my favorite, red M&Ms. But anyways, those are dyes that give that color. What is color? Color is when the white light or yellowish white light from the sun or the lighting in your house hits something, the molecules of what it hits, if there's certain things there, absorb different colors of the light. I think you all remember from high school, I do Ray G. Biv, the colors of the rainbow. Red, green, anyways, you know it. Well, hold on. And here you see the colors of the rainbow. I don't have the actual RGB here. Roy G. Biv, I learned this in high school. And white light makes up all these colors. And when the white light hits it with these colors, some of them are absorbed by the molecules due to the chemical bonds and the way electrons or chemical bonds, certain types, can absorb light. If you look at a carrot, all the colors of the rainbow are absorbed by a molecule called beta carotene, which is good for your eyesight, except the orange. And that's why a carrot looks orange. If you look at a red pepper, all the colors of the rainbow are absorbed except red. And that's because of that. Now, different dyes are made up of different mixtures of these colors, molecules that absorb all the light except that color. Now, what you'll be using and doing today is determining what are the different, or is it pure material in first food coloring and then Kool-Aid, different colors or different types. Now, how do you do this? how do we separate the different molecules or types of compounds in a mixture to identify them? Well, a very old way is called paper chromatography. Now, paper, well, you know what that is. Chrome, color, and graph, so you graph different colors. And this is where you have a small sample, you put it on paper, and then you use a liquid to move things up the paper. All right, warning, warning, I'm gonna do some artwork. Now, usually you cut the paper in rectangles like this. It's supposed to be a rectangle. Near the bottom, you're gonna draw with a pencil a line. And that's the starting point. And say you have red dye number whatever, you're going to put a dot of that with a toothpick right there. And I think on this one, they do one for each one. And then there's going to be some, this is going to go in a test tube. And you're going to have some solvent here. And that's called the eluting solvent. How do I know all this stuff? Because in grad school, I used paper chromatography and other chromatography like this to identify things I was making. And this solvent has to be below this line right here. It's got to be below it. You don't want it. What happens is, well, I'm going Technicolor on you. This liquid here goes up the paper, absorbs it, and moves up that front. You stop and pull this out before the liquid goes up the top. Now, what will happen is, if this right here has different or just one thing, a dot will come here. Sometimes you'll have more than one. And with this lab, when we've done it face to face, it's not going to look as pretty as you'll see in the videos. And when it's done, you take the strip out of here and you mark where this went to, the top. Now you'll have this strip, and here's where your solvent went to. Here's where it started, and here's that dot. Now the distance from where the line was to the top of the solvent, I'll call that A. It's a measurement. Use a ruler, millimeters, centimeter, use millimeters. Now, where you start and to where the center of the dot is, now they have where you can do other ways. Just go to center dot. We'll call that B, the distance. Now, there's a very important measurement you do called RF. This stands for retention factor. And for compound B, or let's call this compound 1, the RF factor for 1 is the distance it traveled, B, divided by the total distance the solvent went, A. And for a number of things, you're going to be calculating the RF value, retention factor. Now, in real life, if you have an unknown or known, this would be known compound, and this would be, and there's your line, unknown. And if you do it and your solvent front goes up to here, let's call this distance A, And both of these, the dot moves up to here. And let's call this distance B, and this distance for the second dot C. So let's call this RF known would be B over A. RF unknown would be C over A. If these are the same, then it's the same compound. And you can use this to identify it. Now, when I was in grad school, wow, that was a long time ago in a galaxy far, far away. Anyways, I used to use maybe 50, 100 of those a week, a lot. There's other methods we also use, like gas chromatography called GC, which I use. And, but because it's expensive to buy, paper doesn't work as well as other material like silica gel on aluminum. Well, that's expensive to buy that stuff. And to save money, we would make our own slides on glass microscope slides. So every morning when I got into the lab, and I wasn't the only one in our research group who did this, my first task was to make, or sometimes I do it Friday afternoon right before I left, depending how lazy I was Friday. Monday morning, I knew if I didn't have enough, I'd make them. And I'd make up about 100 of those by dipping them into a solution of silica gel and water, carefully separating them, putting them on a tabletop, let them dry. Once most of the water is, we had a box with an absorbent desiccator box, and we saved those. Each of us had our own, and you put all your plates in there and keep them dry and use them when you ran a reaction. All right, let's look at what you're going to be doing today. Now, here are the different things you need. You got your Kool-Aid, you've got different equipment over here, and you'll also need the food dyes. Now, let me tell you an interesting story about food dyes. Be careful with them. Wear gloves. Don't touch your face with your gloves on when you're working with food dyes. Now, back when I was in grad school, one of the postdoctoral fellows I really liked, Larry Plavin, Dr. Plavin, gave a Halloween party. And this was in East Lansing, Michigan, in his apartment. Oh, he rented a home. He had his own home. And he invited a lot of people. It was a fun party. And you had to come in costume. I don't remember what I wore, but it was a good costume, I'm sure. Probably came as a samurai. But anyways, this one couple came and they had bed sheets. They made it in togas. They made little wires with light bulbs that lit on their head antenna. And then their face and their arms and hands were all green. And they won the award for the best costumes. And I was standing there, and I didn't know them that well, nice people. I'd met them the first time at that party. And Larry asked them, "How'd you get your skin green?" And the guy said, "We use food dye." Found out later it took about 8 weeks for the food dye to wear off because it had been on their skin long enough. It wouldn't wash off unless you started taking off some of your skin by scrubbing it so hard. So be careful. Food dye will stain your skin, so wear gloves. I can still picture them decades later. They were great, but they also told the story that when they were driving to the party, a policeman pulled up next to them on the road, looked up, scared him. The policeman seeing two Martians. All right, what you're going to do is you'll also need some water. Now, I say pure water. You can use tap water for this. You'll need some table salt, sodium chloride. Remember, please pass the NaCl. And if you have the kosher stuff, that's better. But I don't think if you have the iodized salt, they'll make a difference. You'll need a pencil, not a pen, scissors, paper towel, aluminum foil or plastic bag, I don't know, white paper, transparent tape, I guess, coffee, you use the toothpicks. You don't need the M&Ms or the water soluble because you're only going to do activity 1 and 2. Again, you're only going to do activity 1 and 2. Now, preparation, you've got to make solutions of the Kool-Aid, weigh out 2 grams in your with your scale and your weigh boat, transfer each to a plastic cup, put in 5 milliliters, use your spoon to mix it. Make sure you rinse your spoon before you go to any of the others. They tell you that. You'll need to make 100 milliliters of a 1% sodium chloride solution. How do you do that? You weigh out 1/10 of a gram of sodium chloride. You don't have to spend 20 minutes trying to get a 0.100. You're a little higher or lower, that's okay, but it's supposed to be 0.1 and you're at 1. No, that's too much. And you'll add that to 100 milliliters, which you measure, not weigh, in your graduated cylinder. Mix 2 together, stir it until all the salt is dissolved. You're going to have to cut the chromatography paper in half to make strips like they have here. And they have cut a V like this so it doesn't go into the material. Usually I've always used a flat bottom, but follow the instructions. The micro pipettes you've got to cut so you have more of an opening. Now, at the bottom of each of these strips, you're going to have to put a little above that arrow a line. It's important you do that with a pencil. A pencil has lead in it, really not lead, graphite and clay, which won't separate on chromatography. Ink in a pen is made up of colored materials, and it will separate and it'll mess up your strip. All right, now what you're going to do is follow activity 1. You'll put 2 drops on each of the separate pieces of paper. And here they have put a little on something like a piece of plastic, then put the micro pipette. You can just dip it into your small cup. And then you'll touch the micro tip to the middle of the line drawn, 1.5 centimeters on the strip. And you'll do it a couple of times till it's on the strip, until it's dark. And you'll have a small spot. And here they have a video you can watch how to spot your paper. I'll let you watch it on your own. And then you'll repeat 4 and 5 using separate micro tip pipettes or eyedroppers, really, on other chromatographies for the other 2 dyes. Then place 3 to your test tubes, the larger ones, I guess, or whatever, 17 by 100, and put 20 drops, about 1 milliliter of the 0.1% sodium chloride in each of the test tubes. Then you have straight pins, and the top of the paper, you'll punch it in, the very top, the pin, and that will hold the paper. When you put it in there, that pin will hold the paper from falling down. And you'll put that in there. Now here, carefully lower the chromatography strip with the dye on there into the test tube. And then it should be straight, not touching the sides of the walls. That's why you got the pin. And then allow it to travel up. Now they say 15 minutes. What I would do is just before the wet layer is before the top of the slide. I guess you could let it go to the top, but I have always let it go a little below. You'll then take it out. Now, while it's still wet, you put it on a paper towel or something while it's still wet, you'll measure, you'll be able to see a line like right here. And that's just the wet part of salt water. And you'll measure that distance and record it. Then on yours, you only have one dot, and you'll measure to the center of that dot and record that distance. And the difference would be the RF value for each of the dyes. And measured millimeters, you'll do the solvent front, how high it went after 15 minutes on the paper. Don't let it go all the way to the top. If it's less than 15, take it out. And then if it's more than one color dot, measure each one of those. And here in red, number 40, what was the color of the band? What was the distance traveled? Color, what was the solvent front? Divide the first column by the second to get the RF. And you do that for yellow 5 and blue 1. Now you'll do essentially the same thing with each of the different colored or flavored Kool-Aid solutions, orange, grape, and strawberry. You'll mark a line, make your strip, have separate fresh test tubes, clean out the ones you just used, rinse them out with water, put in your 1 milliliter, 20 drops of sodium chloride, use the micro tip or a toothpick to take the Kool-Aid solution and make a dot that's visible, put it in the test tube, let it go up for 15 minutes. Now here they say in steps 12, you can put them next to the strip from number 1, part 1, to see what colors are in the different Kool-Aids. Or you can just look at the RF values and you would identify it. And what you'll do is each of the bands, like band 1, 2, and 3, what's the distance, what is the solvent, divide the distance of the band, divided by the distance of the solvent, get the RF value, and you look at this table, RF, to see what's the identity. Like, is it red dye 40, yellow dye 5, blue dye 1? You will not do activity 3. Well, if you want, I'm not going to stop you, but you don't have to do it. And let's look at the lab write-up for this lab. Let me open it first. Hold on. All right, let's do this. Sorry about that. And for the write-up, you'll fill in table 1. And here, the question 1, you'll answer. List the 3 you examine in order of polarity. Now, I'll explain that in a second because I didn't. And then you'll fill in table 2, and you'll do this question. Don't forget to include one photo. Now, let's talk about chromatography. Chromatography, you have a piece of paper. What's paper? Well, you learned about paper. Remember how a towel works? Well, paper is made of the similar material, but different than cotton. Both have hydroxyl groups, OH, attached to carbon, and that makes it polar. And you learned about light dissolves light. So if you look at a chromatography, the salt water is very polar. Water, salt are both polar. And that helps move the molecules up the paper. Now, the paper is also polar. Now, the more polar molecules will go slower. The ones that aren't that polar or non-polar will go up quicker. And that's how that works. And now you can answer that question. I guess with that, we're done with the lab. Let me close some things here. All right, let's continue the review for the final. And how I'm doing that review is I am looking at each of the test reviews. I'm going through that and some of the problems. One thing I forgot to mention, if you go to Blackboard, let's go there right now. Go to lectures. And scroll all the way down. Oh, wait, I didn't want to go here. Well, these are where the reviews are. Let's go back to course information, recommended problem answer sets. And now if you scroll down, I have practice problems for the final exam. And these are similar to what I've done. And you should be able to do all these practice problems so you can do well on my final exam. Let's take a look at this. And you'll see, let me get it on the screen for you. You'll see these are the same problems I've been going through, and you should be able to do all these. I even have organic chemistry there, some of them. And I would use your test also. Let me just talk about something. The best way to study for the final exam, go through in those final exam recommended problems. Also, the best way is you should have copies. And if you follow along, and I also send out a link where you can see the answers in a private video, you should have gotten that you should use each of your exams as practice problems. Go back and do exam 1, 2, 3, and 4 now, and that will be good practice problems for the final exam. If you look at the practice problems we've done all semester and look at the hourly exams, they're similar. Are they the same? No, but they're similar. Am I going to put the same problems from the hourly exams on the final? No. Am I going to put similar ones? Of course, that's what we practice. So your hourly exams and the practice problems, especially the practice problems for the final exam, you should practice those because that way, if you can do those correctly, you'll be set for the final. Now, if I look at the clock, let's take a 5-minute break and we'll come back and start with test 2, the last material, and go over that. let's get going. This thing shows up every piece of dust everywhere. All right, let's go back to review. We're doing test 2 review. We had just did the mole and these relationships and know how to do these conversions you should be familiar with. We've done that. Don't forget, you should use your good buddy, your good friend, unit analysis. Now, let's look at the practice problems for this. Wrong one. All right, why isn't it open? Hold on. All right, let's look at number 4. For the following reaction, how many grams of C3H8 propane are needed to make 24.6 grams of CO2, carbon dioxide? And here's you're given a balanced chemical reaction. Remember, the coefficients, the number in front, give you molar ratios. When there's no number, it's the number 1. So if we look at this reaction, what it tells us is 1 mole of C3H8 reacts with 5 moles of oxygen to make 3 moles of CO2 and 4 moles of water. Those are molar ratios. Probably one of the most important things I know in chemistry. So here we're trying to find how many grams of C3H8. We're given grams of CO2. We're given a balanced chemical equation. There's no way in one step I can go from grams of CO2 to grams of C3H8 propane. You can't. So what do? Well, first of all, you wait for Dr. White to open up something else. You look at important information. Let me get it up on the screen. Excuse me. Important information, final exam, and you have mass calculations. Mass means grams for reactions, meaning balanced chemical equation. And there are 3 steps. Whenever you're given the mass, the weight of, you convert that to moles. Next, what you just converted to moles in step 2, you convert to moles of what you're trying to get to, that compound. And finally, in step 3, the moles of B you just calculated, you convert to grams of B. So let's look at that. All right, so in step 1, we're given grams of CO2. We have to convert that to moles of CO2. You have grams of CO2 going to moles, and use your good buddy, your good friend, unit analysis, whatever you're trying to get to, the units go on top of a ratio. Whatever you're trying to get rid of, the units go underneath. And where do I get a relationship of moles of a compound and grams or weight of a compound? Well, in case you forgot, you look at important information, test final exam, and 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So what's the molecular weight of carbon dioxide? 1 carbon, 2 oxygens. You already learned how to go to the periodic table. 1 times 12 is 0.0, is 12.0. The oxygen atomic weight is 16. 2 times 16, or 16.0, is 32.0. Add them up. They both have one significant figure to the right of the decimal. So your answer should have one significant figure to the right of the decimal, 44.0, and you put it in. Notice grams of CO2 divided by grams of CO2 cancel out, become the number 1, and you're left with moles. Now, in a multi-step calculation, there are 2 philosophies that I told you. One, round off at each step, and I'm a round off at each step person, or you round off at the end. I will calculate it both ways for a problem like this or a multi-step problem on the final. And remember, on the final exam, like on the other exams, it said, please use proper significant figures for all calculated answers. 3, exact number is 1. 3, you get the same number of significant figures in your answer as the number you're multiplying, dividing by that has few significant figures, 3. Now, in step 2, whatever you just calculated, moles, you convert now to moles of what we're trying to get. In this case, we're eventually grams of C3H8 propane, but at this step, you want to make moles of C3H8 propane. So we start with, in step 2, 0.559 moles of CO2, which we determined in step 1. We want to get the moles of C3H8. Use your good buddy, your good friend, unit analysis. Wait a second. Use your good buddy, your good friend, unit analysis, and what you're trying to get to goes on top of the ratio, and what you're trying to get rid of, the units, in this case, moles of CO2, go underneath. Where do you get a relationship between moles of C3H8 and moles of CO2? The balanced chemical equation. And what this tells you, the coefficient when there isn't any is 1. 1 mole of C3H8 makes 3 moles of CO2. 1 mole of C3H8 makes 3 moles of CO2. And therefore, 1 mole of C3H8, and you put 3 moles of CO2. 1 and 3 are exact numbers. Ooh, itchy eye. Hold on. All right, it's done. All right, 1 and 3 are exact numbers and don't play a role in determining significant figures of the answer. And the only one you have here is this, 3 significant figures. Your answer is 3 significant figures. Are we done? No. How do we know? Because we're trying to get the grams of C3H8. And now we'll do step 3, moles of whatever we calculated to grams of what we're trying to get to. In this case, C3H8. Well, we have our moles of C3H8. We want to get the grams of C3H8, and we'll use our good buddy, our good friend, and it has been mine for many, many years, many years. The grams of C3H8 go on top of this ratio. The moles of C3H8 go underneath. And where do you get that relationship? You look at important information, final exam. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights in grams. So 1 mole of C3H8 equals the molecular weight in grams of C3H8. And over here, MW, shorthand for molecular weight, C3H8 is the sum of all atomic weights of the atoms in that molecule. 3 carbons, 8 hydrogens. Remember, for the final exam, Use 3 significant figures for all atomic weights. And yesterday I went through and showed you how to round off what's on the periodic table. For carbon, it's 12.0. There are 3 of them, 36.0. For hydrogen, each hydrogen is 1.01 to 3 significant figures. There are 8 of them, 8.08. You add it together, you get 44.08. Remember, when you add, you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures to the right of the decimal. Well, here, this is 1 to the right of the decimal. This is 2. What's the lowest number? And time's up. Hopefully you pick 1. So now you round 44.08 to 1 significant figure to the right of the decimal. Keep the 0, use the 8 to round off. Is that 4 or less or 5 or higher? Time's up, 5 or higher. You drop that and the number in front, the 0, you increase by 1 to 0.1. So that's 44.1. Put it in there. Notice moles of C3H8 divided by moles of C3H8. The unit cancels out. I like that. Cancels out. You're out of here. All right. And you're left with grams of C3H8. And this is 3 significant, 3 exact number. Answer is 3 significant figures. And if you had rounded off at the end, you'd get 8.22. Oh, I forgot to mention 10 points. If you look at test number, this is test number 2. And we don't need this anymore. Let's see, anything else? And I have a few others you should look at. And if you look at the practice problems final exam, oh, I have a problem here similar to what I just did. And you should know how to do that. And if you notice, I have some balanced chemical equation problems for you to try also. And you can also go to test 2, the various chapters, practice problem sets. All right. Let's continue on and let's talk about test number 3 review. First, we talked about gases and we talked about pressure and key pressure. And let me close a few things. And let me open something. All right, we're all set up. All right, we're ready to go. Now, gas is an important measurement of gas is pressure, force per unit area. And the measurements, units, and this should be changed. I didn't change it. The unit of measure is millimeters of mercury. And in honor of the great Italian scientist Torricelli, or Torricelli, I think it's pronounced, we also have the unit torr, T-O-O-R. And 1 torr equals 1 millimeter of mercury. Now, another important measurement is atmosphere's pressure, ATM. And 760 torr, by definition, at sea level, at 760 torr with no storms coming through, equals 760 millimeters of mercury equals 1 atmosphere. And that's not what I want. And here I have a series of problems. Let's look at number 3. How many atmospheres is 741 torr? We're trying to find ATM. We're given 741 torr. And you'll say, I only have 741 torr to start with. If I can convert this in one step using a ratio to atmospheres, using unit analysis, what would go unit-wise on top of the ratio, ATM? I want to get rid of torr. That would be on the bottom. And where do I find the relationship between atmosphere and torr? I have it here, 1 atmosphere, 760 torr, 760 millimeters of mercury. And 1 atmosphere, 760. Now remember, 1 and 760 are exact numbers. Torr here is 3 significant, and your answer should be 3 significant. And if you notice in number 4, we're trying to find how many torr is 1.237 atmospheres. Here we have torr. We're trying to find, we're given atmospheres. We start with the atmospheres. We're trying to get the torr. We can use a ratio. What goes on top of the ratio? Use your good buddy, your good friend, unit analysis, torr. What goes underneath? Atmospheres. And where do we get this? 1 atmosphere equals 760 torr. Put in the numbers. Remember, 760 and 1 are exact numbers. 1.237 is 4 significant figures. And notice my answer is 4 significant figures. Now, your calculator, if you did this, you might have seen 9.401 times 10 squared, which I've just put that into scientific notation. This is some skill. If you look at test 3, I ask questions like that. Now, next I talked about the gas laws, and these are mathematical relationships dealing with various parameters of gases. The first one is Boyle's law. P1 times V1 equals P2 times V2. P1, initial pressure. V1, initial volume. P2, final pressure. V2, final volume. And in a Boyle's law problem, you'll be given P1, V1, and either P2 or V2. And the one you aren't given, P1, P2, or V2, you'll want to solve for using Boyle's law. And let's look at an example. If we look at number 6, if a balloon has a pressure of 654 torr and a volume of 1.894 liters, L is liter volume, what is the pressure of the balloon if the volume is increased to 5.133 liters? Well, the first, a balloon has a pressure and volume. Those are your initial pressure and volume. P1, 658 torr, V1, 1.894 liters. What is the pressure after you change the volume? Well, you're trying to find P2. And that new volume is the final volume, V2, 5.133 liters. So how do you do that? use Boyle's law. Remember, that's important information. Let's take a look just to make sure I'm not lying to you. Have you noticed I haven't lied to you all semester? I don't lie. If you look, here is Boyle's law. And that's on purpose because I've cut down on memorization. I have P1 times V1 equals P2 times V2. You're trying to solve for P2. How do you do that? You get it alone on one side. When two things are multiplied to get one of them, get rid of one, divide by that. Anything divided by itself is number one, which means 1 times P2 is P2. So I divide this side by V2, but whatever you do to one side, you have to do to the other. And I divide that by V2. V2 over V2 is 1 times P2 is equal to P2, and that's equal to P1 times V1 divided by V2. And I've just rewritten it underneath the OR, that's OR. I forgot, some of these I still use cursive. And P2 equal P1 times V1 over V2. And you put those in. Notice liters divided by liters cancel out. You're left with torr. And again, multiplication division. You get the same number of significant figures in your answer as the number you're multiplying dividing that has the fewest significant figure. 3, 4, 4. 3 is the lowest, and your answer is 3 significant figures. Now, if you have your calculator set to scientific notation, you may see 2.42 times 10 squared. Let's continue on. And the next thing I'd like to talk about is the ideal gas law, PV equal nRT. P is pressure, but it has to be in atmospheres. V is liters, the volume. N is the number of moles, and we just went through how to do moles from grams. T is the temperature in Kelvin, and R you'll be given is the universal gas law constant, and this is a measured number, and for this class, you'll use 0.0821 atmosphere liter mole K, which is 3 significant figures. And if we look at number 10, if you burp, oh, I almost did burp. If you burp 86.75 grams of CO2 at 545 millimeters of mercury, 34.6 degrees C, then what is the volume of your burp? Oh, there's something missing from the problem. 15 points. Yep, 15 big ones. And remember, on test 3, there was a PV equal nRT, 15 big ones, 15 points. So if you read this problem, we're given a weight, grams of CO2, a pressure, 545 millimeters of mercury, a temperature, and you'll learn later you need R, which you'll be given, and you're trying to find volume. Notice, none of those measurements change. Notice, none of those measurements change, and you're being asked to find something about a gas. That immediately should tell you ideal gas law, and this is important information, final exam, PV equal nRT. And the important thing is each of the things, pressure, volume, well, you're going to calculate volume, number of moles, temperature, you have to have in the right units. But I have never seen a gauge that measures atmospheres, but I have seen torr in millimeters of mercury. I've never seen a balance that measures moles, but I have seen one that does grams. And I've never seen a temperature device, thermometer, or an electronic thermometer that measures in Kelvin. It's degrees C. So you're going to need some things, and one of them is Kelvin equal degrees C plus 273. This conversion we just went through using 760 torr equals 760 millimeters of mercury equal 1 atmosphere. So let's get to work. We have PV equal nRT. We're trying to solve for volume. We want it alone on one side. Therefore, how do you get rid of P? Divide by it. Anything divided by itself is the number 1. Whatever you do to one side, you do to the other. And now 1 times V is V equal nRT. Now, the pressure has to be in atmospheres, but you're given it in millimeters of mercury. So as we just saw, you take millimeters of mercury, you want to go to atmospheres, use your good buddy, your good friend, unit analysis. Atmospheres goes on top of the ratio, millimeters of mercury goes underneath. 1 atmosphere equals 760 millimeters of mercury. That's where we get these numbers. These are exact numbers, 3 significant figure. Answer, pressure for PV equal nRT, or the P in nRT divided by P is 0.717 atmospheres. Temperature we use here has to be in Kelvin. And if you forget, remember years ago, my students had to memorize this. Notice important information, final exam, T, temperature, has to be in Kelvin, and you're given the formula to convert that. By the way, don't tell anybody I'm doing this and being nice. I don't want to ruin my image around here. So temperature in Kelvin, 34.6 plus 273. Now notice you have 1 past the decimal, and 273 is an exact number. So you get 307.6 Kelvin. Now the last thing we need to do is find N. N is moles. Moles of CO2. But we're given a weight. Well, we just did one of these. Let's do it again. You're given a weight of CO2. You want to go to moles of CO2. Whatever you're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get that relationship? Moles of a compound, grams of a compound? You're right, important information. And 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights in that compound. So we need to convert this, and we need to go from grams to moles. Use your good buddy, your good friend, unit analysis. Moles of CO2 go on top. Grams of CO2 you want to get rid of go underneath. 1 mole of a compound equals the molecular weight. Over here, 1 carbon. The atomic weight is 12.0. 2 oxygen, each one 16.0. That's 12 plus 32.0. 12.0 plus 32.0 equals 44.0. And 3 significant, the number 1 exact number, 44.03. When you multiply and divide, you get the same number of significant figures in your answer that has the fewest significant figures, and that is 1.97, 3 significant figures. Now, in PV, V equal nRT, N is moles, calculated here, 1.97 moles. R is the universal gas constant, 0.0821 atmospheres liters mole K. That's given to you important information, final exam. And the temperature Kelvin is right here. And the pressure in atmospheres, we calculated right here, 3, 3, 4, 3. My answer has 3 significant figures. If you wait until the very end to round off, or you round off at each step, you'll get the same answer both ways. And don't forget, PV equal nRT tells you when to check. And in the winter, temperature goes down, V, N, and R are constant in your tires unless you got a blowout, and I hope you don't. The temperature goes down, the pressure in your tires go down. You should check it. And also in the summer, real hot coming up. I hope we don't have a hot summer. The temperature goes way up, volume, moles, and R stay the same. Therefore, your pressure will go up. And so PV equal nRT tells you when to check your tires, winter and summer. You should check it the rest of the time too, but that's really important. All right, and finally, Dalton's law of partial pressure. The total pressure of a mixture of gases is the sum of the partial pressures of each gas. Partial pressure is the pressure of that gas in that mixture if it were alone. And I'll let you look at the problem in there. All right, now we talked about something important, and when you have something boil, here we have water on a hot plate, in a beaker, and it's boiling. And you see these little bubbles that come to the top and they collapse and they give off water vapor. And that water vapor is a gas that has a pressure. When that water vapor equals the atmospheric pressure, that's the boiling point temperature of that liquid, in this case, water. Now, because the boiling point is when the pressure, vapor pressure equals atmospheric pressure, if you lower the atmospheric pressure, you need less gas pressure. Therefore, it boils at a lower temperature. And you should know, which I asked on test number 3, the higher the altitude on the Earth, the lower the atmospheric pressure, and therefore the lower the boiling point of the liquid. Now, next we talked about solutions. And solutions, you should know, is a mixture of 2 or more chemicals or substances, same thing, where neither or none of them lose their chemical identity. In other words, when you mix them together, they don't react. And when we talk about solution, there's a solvent, and those are components. That's the component present in the greatest amount. All other components are called solutes. So if I take sugar and water and I have 10 grams of sugar and 100 grams of water, sugar is the solute because it's present in lesser amount than the component water, which is a solvent. Now, water doesn't always have to be a solvent in a solution. Sometimes it can be a solute. Now, something that you may think is a solution, but is not, is a colloidal dispersion. And that's where you have small particles of one compound dispersed in another. And how do you tell that? It's not a solution because it will scatter light. Ooh, I get to show you one of my fancy flashlights. I'm a flashlight collector. This is made by a great gentleman in China, Hank Wang, who's making probably the best flashlights in the world right now. And bright one. Notice if this is my hand were a solution, you don't see any light come through, and that's because the particles are stopping it. If it were a solution, say I had sugar and water in here, the light comes through. Now check this out. Hold on. And can you see it? I don't know if you can tell. It's now green. I don't know if the color comes out that well. Can you see a green here? Might be too bright. I'm green. It's one of my favorite flashlights. K93, Noctagon K93 by Hank Wayne. I'll have to email him and say, you can watch me talk about one of your flashlights in my class. All right. Now, what are examples of colloidal dispersions? Well, milk, blood, latex paint, mayonnaise, butter are all colloidal dispersions. Now, next I talked about like dissolves like, and that is like solutes are soluble in like solvents. What we really mean are polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. And what's polar? Water, salts, and alcohols. These are examples of something's polar. What are nonpolar substances? Vegetable oil, gasoline, Vaseline, and baby oil is another example. There are others. And if you mix water and vegetable oil, they don't mix, they separate. And know this. Now, there were some terms I asked you to learn. What's the solubility of a solute? That's the maximum amount of solute that will dissolve in a given amount of solvent. One more, and it precipitates to the bottom as a solid. Saturated solution, you have a maximum amount of solute that can be dissolved under the conditions the solution exists. Dilute solution, you have a tiny amount of solute present compared to what amount that could be dissolved. Concentrated, you have a lot of solute present relative to what could dissolve. And finally, aqueous solution. And an aqueous solution is shown by bracket, AQ, close bracket. And that means the solution in which water is the solvent. Now, when you talk about solutions, important concept is, excuse me, concentration of a solution. How much solute is in a certain amount of that solution? And molarity for chemists is the most important concentration measurement. Molarity, by definition, is moles of solute per 1 liter of solution. But 1 liter is 1,000 milliliters. Therefore, we can say molarity is moles of solute per 1,000 milliliters of solution. Wow, very important. Know this. And if we look at practice problem part 2, chapter 5, part 2, dealing with solutions, And give an example of colloidal dispersion. I just did that. Give an example of solution, pop. That's the stuff in a can or bottle that's carbonated. Dr. White's from the Chicagoland area, and we call that pop, not soda. And you can put down soda too, I would know. Air is a mixture, gasoline, tea, your mouthwash. There are a whole lot of mixtures or solutions, I should say. And here I went through identify the solvent and solute. Now, what does 1.34 capital M HCl mean? Capital M tells you molarity, moles per 1,000 milliliters. Therefore, that means 1.34 moles of HCl per 1,000 milliliters. And if we look at number 7, what does 4.56 times 10 to the third capital M NaCl bracket AQ close bracket mean, and what is the solvent? In this case, capital M tells you molarity, moles of solute per 1,000 milliliters. The solute is 4.56 times 10 to the third moles of NaCl, sodium chloride, and that's per 1,000 milliliters. If you put 1 liter, I would mark that correct too. And now we have solvent. What is that? The bracket AQ close bracket tells us that. Now let's look at number 8. How many moles of sodium chloride are in 125 milliliters of a 3.45 capital M NaCl solution? And as I've taught you all semester, what are we being asked to find? I use a question mark to identify that. Moles of sodium chloride. What are we given? 125 milliliters of that solution. And we're given this number 3.45 capital M NaCl. Immediately I see the capital M, I think molarity, moles of solute per 1,000 milliliters solution. And I write 3.45. What this means is 3.45 moles of NaCl per 1,000 milliliters. So I have the 125 milliliters. I want to get to moles of sodium chloride. If I could do this in one step, what do? Well, I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of this ratio. Whatever I'm trying to get rid of goes underneath. Where do I get these numbers? From knowing 3.45 capital M NaCl means 3.45 moles of sodium chloride per 1,000. And I put in the 3.45 and the 1,000. Now, milliliters divided by milliliters cancel out. You're out of there. And I'm left with moles of NaCl. Yay, that's what I want. And now I'll do the math. And remember, when you do multiplication division, you get the same number of significant figures in your answer as the number that has the fewest significant figures. And we have 125, 3 significant figures. 3.45, 3 significant figures. Now, the 1,000 is part of the definition. Therefore, 1,000 is an exact number that does not play a role in the final calculate, determining how many significant figures in your answer. Therefore, you have 3, 3. Your answer should have 3, and it is. If I look at the clock, I think this would be a good time to stop. Let me remind you, hopefully you've already handed in test 4. Don't forget, the lab last week is due today. I forgot to mention, I better do that now. And I'm actually going to change it live and you can watch me. this, because it's the end of the semester, instead of being due next Tuesday, I need this by next Saturday. Please, that's the deadline. That way I can grade it and get all your grades ready next week when I'll be busy doing grading your final. And let me save this. So today's lab is not due a week from today, but is due this Saturday. And please get it done by then. And with that, tomorrow, if people show up, I'll give you a tour of a chemical plant, but I'll cut it out of video and I won't post a private video. And tomorrow is our last lecture of the semester. Boy, this semester just goes zoom. But anyways, thank you for being in my Chem 1 1105 class. And with that, don't forget, I have office hours tonight and tomorrow night from 6 to 7:15 on Zoom. And I'll say, gehen gesund, which means go in health. Gehen gesund, goodbye. Stole that from Granny to Beverly Hillbillies.